Okay, this is the first of 3 videos for Chapter 5. We're going to cover the first 3 sections here. I really like Chapter 5. I think there's a lot of interesting mathematics here, and it really sets the stage for some very neat stuff that happens down the line, some of which we'll see much later in this course, and some of which is even beyond our scope. You can see down at the end, we're going to get into ideas of infinity, which is always fun. Okay, section A, not too tough. We're talking about number sequences here, just patterns of numbers. And we need to be able to recognize those patterns, describe them. We'll talk about that in a moment. And then, of course, once we understand them, we should be able to continue patterns, both forwards and backwards. We use in this course U sub n to represent a sequence. That's sub as in subscript, which is what the letter n is here. So it's not a superscript like an exponent. It's down below. So U sub n is going to represent any of our sequences that we look at, and then we use numbers in place of n to describe which term of the sequence we're talking about. So U sub 1 would be the first term, U sub 2 is the second, and so on. So how can we describe a sequence? Well, we should be able to list out the terms, so just with commas, and then we use a little dot, dot, dot to show that the sequence continues indefinitely. We could use words. We could just describe it using English. But again, we're mathematicians. We don't want to have to waste our time speaking or writing down these phrases. We want to be able to use math. Right? So what we're really going to focus on for the most part is this third one here, which is using an explicit formula, or nth term formula, or general formula, whatever, which is just a rule which tells us what a particular term is based on the n value. And you see the example that we're looking at here, it looks kind of like a linear equation, right? It kind of looks like y equals x plus 2. And we'll come back to that in a minute or two. But that just tells us there, you know, hey, if I want to know the fifth term, I put in 5 for n, and then I add 2 to that, and then I get 7, and yeah, oh yeah, look at that. 7 is the fifth term. Cool. And then you could connect that idea to a graph here. Of course, this graph is not of a line with connected dots because our values in the sequence are only integers, so it needs to be a discrete graph rather than a continuous one. Now, one more note about formulas. This example here is an explicit formula, which is great. I mean, that's really the best one. That's what we want. There is, however, a different type of formula which goes by a few different names, and all that does is it tells you what a particular term is, but based upon the term that came before it. So if we look at this particular sequence over here, we notice that it's going up by 1 every time. So we might say U sub n is equal to U sub n minus 1 plus 1. So that tells us that a given term, the nth term, is equal to the n minus 1th term. That's the term that came right before it, and then, but it's 1 more than that. So a recursion formula is easier often to come up with because you just look at the pattern and recognize, oh yeah, each one is 1 more than the one before it. But it's more difficult to figure out than obviously what a particular term is. I can't figure out what the 100th term of the sequence is here without knowing what the 99th term is first, whereas with an explicit formula, we just put 100 in for n and we're good to go. It's 102. All right, so we're going to now move into special types of sequences. And that's what we'll spend the bulk of this video talking about. So we're going to have arithmetic sequences and geometric sequences, and then I'll talk at the end about a few other special types that some of which you'll know about and some of which I don't think you will. So an arithmetic sequence is just one where each successive term differs by a common difference. In other words, we're adding or subtracting the same number every time. So the example we just saw was an arithmetic sequence where the common difference was 1. Little historical note here in the middle section on where the name comes from. If we had an arithmetic sequence with 3 numbers, a, b, and c, then that would mean that the difference between b and a must be equal to the difference between c and b. And then from there we can derive this statement and then this one here, which tells us that the middle term is equal to, well, you might see that as just the average or the mean of the two terms on either side of it, but it is specifically something called the arithmetic mean. Historically, there are three different types of means, and the arithmetic mean is the one that we tend to refer to in common practice when we talk about the mean of a set of numbers. Anyway, that's where we get the name from. Down here, we've got a formula which appears right at the top of page 3 in SL 1.2. It's actually the very first formula in the book. So that's the general term for any arithmetic sequence can be found by taking the very first term and then adding that to the whatever term number we're interested in, but minus 1 multiplied by the common difference. That should hopefully make sense, right? If we wanted to know the second term, for example, then we would take the first term and then add to that. N minus 1 in this case would be just 1 times the common difference. If we wanted the third term of the sequence, then n minus 1 would be 2, so we'd be adding 2 common differences to the first term, and then we'd add 3 common differences to get the fourth term, and so on and so on and so on. And again, you should see in this the format of a linear equation, where d is actually a constant, u sub 1 is a constant, and our two variables would be, that would be like our y value, and that right there would be our x value. For some of you, I think that'll just help you make sense of this. If you just know, oh, arithmetic sequence, I can think of that as a line. That'll help you wrap your head around what's happening here. Anyway, let's just take a look at a few simple examples just to make sure this all makes sense. And it's all going to be about this formula, so make sure that you've got it in front of you. Okay, so we got a sequence. This first one's pretty boring. Show that the sequence is arithmetic. I don't really like that question. We're assuming that the pattern of adding 7 will continue forever. As far as showing that the sequence is arithmetic, that's all we're going to say is the difference between any two terms is 7. And you'll notice that here they show all 4 of the differences, and that's important. It would not be sufficient to show only that the difference there is 7 and the difference there is 7, because the differences might not all be 7. So we need to show all of them if we're going to justify that the sequence is arithmetic. This example I've jotted down to the right certainly is not arithmetic, so I wouldn't want to just look at those 2 common differences and say, oh, hey, look, it's always 7. It's clearly not always 7. Anyway, B, finding a formula for the general term, u sub n. Okay, so u sub 1 in this case is going to be 2, and the common difference is going to be 7. We've already established that, so we're just going to put those into the formula, and there's actually an answer for C as well. So finding the 100th term of the sequence, we're just putting 100 in for n. Easy peasy. Hey, notice, by the way, they simplified this to make it look even more like a line there. Of course, you're allowed to write your answer in like mx plus b form if you want to. And D, okay, are these 2 particular terms actually in the sequence? Well, probably one is and one isn't. We're just going to put them each in for u sub n, and we're going to see, do we get an integer out for n? And yeah, in fact, 828 is, but 2,341 is not. A little more interesting here, now we don't actually have concrete values. We've got expressions with variables. We're told that these are in an arithmetic sequence. So anytime that I'm told 3 values are in an arithmetic sequence, I want to know what the common difference is. So we should start there and set the common differences equal to each other, and then realize, oh, hey, you know what? We can solve for k now. Great. Next up. Okay, sometimes we're just told specific terms in the sequence, and we need to figure out the other stuff. So in this case, we're going to figure out what D is first, and then we're going to figure out what U sub 1 is. Now, I would not solve this the way that the book is about to show us, but it certainly works. They're using this formula that we had before and putting in what we know about u sub 3 and u sub 8 into that, and then solving a system of equations to work out what both d and then u sub 1 are simultaneously. And that's fine. If it were me, I would just do d alone. So I'd say, hey, look, to get from u sub 3 down to u sub 8, we need to subtract 5 of the common differences to get there, right? 8 minus 3 is 5. And in this case, we're going 8 minus 5d is going to give us negative 17. And then from there, you can easily solve that d is equal to negative 5. And then you can jump into that formula there to figure out what u sub 1 is. But whatever works for you. And I don't know, I guess we could make our own arithmetic sequence. Okay, so we want to put 4 numbers, obviously evenly spaced, in between 3 and 12. So again, that means to get from 3 to 12, we're going to be increasing, if there's 4 numbers in between, that means we're going to be increasing 5 discrete times. So 3 plus 5 common differences is going to get us to 12, and that will tell us what the common difference is. So 9/5. Great, and now we just need to figure out what those numbers are. So we're just going to add 9/5 or 1.8, whatever, to 3, and then keep adding 1.8. Awesome. So there's whatever. There's some junk you can do with arithmetic sequences, and huzzah. Now in the real world, data is not often so pretty, so we may have to approximate using arithmetic sequences to make predictions about a situation. There's nothing really too challenging to that. Here's an example of it. So, if we were looking at the combined mass of a bunch of people, obviously every person doesn't weigh the same amount. But if we look at the totals there, we can get an average, an arithmetic mean, if you will, of the group of people, and then we could use that to predict approximately, how much would the mass be if we had whatever 10 people or something like that. Hey, section C, now we're talking about geometric sequences, and this is just going to be a sequence where we are multiplying or dividing by the same value each time to get from one term to the next. We call that number the common ratio. We use the letter R for it. So with arithmetic, we could take 2 terms and subtract 1 from the one before it to get the common difference. Here, we're going to be using division from a term to the one before it to get R. I mentioned before there were multiple different types of means historically, so we have a second one here called the geometric mean, in which you multiply 2 numbers together and then take the square root of the product, or if there were 3 numbers, you take the cubed root of the product, and so on. And we see that if we have 3 terms in a geometric sequence, that the middle term ends up being the geometric mean of the 2 terms on either side of it. And another formula that is in the data booklet, again on page 3, this time in SL 1.3. This is the 3rd formula in the entire thing. There is our explicit formula for a geometric sequence. So again, to get the second term, for example, you would end up multiplying the first term by 1 common ratio. To get the third term, you'd multiply the first term by the common ratio squared, and so on. So again, we're going to use this formula in the next few examples. Let's go. So here again, this is the same stuff we saw before, right? So show that the sequence is geometric, so we're going to show that the quotient of each of the successive terms is always the same number, so 1/2. So now we have the common ratio and we have the first term. That's all we need. We're going to put those into the formula to answer part B. We see 2 different forms of it here. They're both the same thing. And we can use either one of them to get our answer for part C. Okay, this one again. So we got three terms. They're in they're in a geometric sequence. So we're going to set the common ratios equal to each other. We'll take that quotient, set it equal to that quotient, and then we're going to solve for k. Now we end up, whoa, color changing, very exciting. We end up, when we do this, we will often get a quadratic out if we've got a variable in all three terms, of course. Um, so in that case, we can get two different values for k, and then we're going to get two different common ratios that go along with that. And that's totally normal, nothing to be alarmed by. This problem again, right? We got two terms, so we need to do all the work to figure stuff out. Okay, again, the book is going to use a system of equations and then use that to solve for the r and u sub 1. If it were me, I would say that u sub 2, that's negative 6. I need to multiply that by the common ratio cubed in order to get u sub 5. And then I would just divide by negative 6 and take the cube root to get r from there. And that obviously looks pretty similar to what they've got going on over there. But again, whatever, you want to use the system or not, doesn't matter. And then problems like this are actually pretty common, this whole idea of like finding something that exceeds a particular value. So we've got a sequence which, I don't know, we're left to figure out what type of sequence it is. Hopefully it's pretty obvious that it's geometric. We're multiplying by the square root of 2 each time. So we're going to start off by getting the explicit formula for that. And then we need to figure out, okay, when is this? For what value of n do I get u sub n being bigger than 1,400? All right, and we're obviously going to use technology to do that. So I'm going to graph this. And instead of n, I'm going to use x. And yeah, that is the same thing, right? I just changed the square root of 2. I wrote the 2 as a fraction there. Whatever, it's the same thing, I promise. Okay, so I need to figure out when this is going to exceed 1,400. So 1,400 is actually the second function that I put in, and that is a horizontal line that is way the heck up there. So I think a good move is to not zoom out. That's kind of messy sometimes. I would just change the window settings, and let's change my y max here instead of that tiny number. Let's go up to 1,500. Okay, so now I see my horizontal line, and I still see my other curve down here. They're going to intersect somewhere out there, so I'll just do the same thing. And I need to change my x max. I don't know, I'll go for 100. That should be far enough. Definitely was. And now I'm going to calculate the intersection. Analyze graph, intersection. We've seen this before. Lower bound, upper bound. Okay, my x value here is 16.7. So that means that the 16th term is below 1,400 and the 17th term is above 1,400. So I want to figure out what the 17th term is. Before I do that, I'll just show you there's another way we could have done this. Rather than graphing the horizontal line and finding the intersection, if I just have this first function in there, I can go to menu and then open up a table. And then I'm just looking in this column, because this is the column for f1, which was my function. And I'm just looking for a value in here that is bigger than 1,400. And there it is. It's the 17th term, and this actually tells me exactly what it is without me having to consult my formula. It's 1,536. Of course, that's what I would have gotten had I put 17 in for that n. Okay, and that's pretty much it here. One thing I know I meant to say earlier and I forgot to was our convention is that we're always going to begin with u sub 1, but there's no rule that a sequence has to begin with u sub 1. There are times when it makes more sense to begin with u sub 0, and we'll see some of that in the next video. Generally, we use u sub 0 when we're dealing with some sort of time element. And those of you who are adept at computer programming may recognize that a lot of programming languages. When you count, you always begin at 0. So it's not necessarily a hard and fast rule there, but it certainly is what we will tend to do in this course. Now, I just wanted to finish up with just a few other sequences that I'm sure you know of quite a few of these. The first one, those are the prime numbers, or at least the first 6 prime numbers. There's certainly no recursive nor an explicit formula for those, but that doesn't mean that we don't understand what the sequence is. And we know that it goes on forever, and we know quite a few of them, but we actually don't know how to predict what the next one might be based on the previous one. So anyway, that's a famous sequence. The one below it, just as famous, I would say. That's clearly the Fibonacci sequence. It does, of course, have a recursive formula. I've written it down in 2 different ways there. But regardless, it says that if I add up 2 terms, then I get the next term. And it also does have an explicit formula. So you might not have known that one. Now you do. I'm happy to prove that later on once we've covered mathematical induction. That's one of my favorite induction proofs to do. Then we've got the one down below is, this is a stupid sequence. I don't know. If you've seen it before, it's obvious and it's dumb. This is called the look and say sequence. You look at a term and you say what you see. I see there 1, 1. There I see 2 1s. There I see 1, 2, and 1, 1. Hopefully you get it at this point. Here I see 1, 1, 1, 2, and then 2 1s, and so on. And that's whatever. That's a stupid sequence. But the point is, there's lots of other sequences out there. Our course is just covering arithmetic and geometric, but there's lots of really cool stuff out there. In fact, there's a couple of other sequences that I'm holding back because I'm going to share some of my all-time favorites in classroom problem sets with you. And if you're really into sequences, you should head on over to this website, oeis.org, where you can learn all about your favorite number sequences, or you can use it as a tool to help you learn about a sequence that you're staring at. So if I was really confused by the sequence that I just showed, I could just enter in, I think 4 terms should be enough, and this will search a gigantic database of integer sequences. And well, it's got 6 different results, but the most famous one right up top, the one it's suggesting, is the look and say sequence that I was just referencing. Now there are going to be other sequences down below that also start with those same numbers. So obviously, the more terms you can put in, the more precise of an answer you'll get out. But in this particular instance, I was thinking of certainly this one. And it's not just a cool website to play around with. You can use it to help you solve problems that you're working on. Maybe not IB problems, but just problems in general. I was working on something not long ago. I had some big drawing happening, and I was trying to look at patterns as the drawing got larger, and I had identified a sequence of numbers that seemed to be growing somewhat predictably, but I couldn't work out what the formula was. So rather than spend hours and hours on that, I just popped over to OEIS. I entered in the first bunch of terms that I'd worked out, and then lo and behold, it provided me with an explicit formula to use, and it even referenced the exact problem that I was trying to solve in its historical context. So I got to learn a little bit about where the problem came from, and hundreds of years ago, and who worked on it the first time, or who solved it anyway. So yeah, sometimes you need to work smarter rather than harder. In fact, that's today's quote. Work smarter, not harder. Anonymous, Mike Ropke.